At Parkes, in New South Wales, stands one of the most important radio telescopes in the world. Australian radio astronomy began in the 1940s. Several small instruments were built, and then this great 210-foot dish at Parkes was constructed. It's been in action now for more than 30 years, and is as good as it was when first set up, perhaps even better, and it's been responsible for many major discoveries.
Over the years, this telescope has made so many discoveries, it's very, very difficult to mention them all. One of the earliest reasons for building this dish, of course, was in order to map out the southern part of our galaxy in the neutral hydrogen line. That is, to estimate how much neutral hydrogen there is, which, of course, apart from stars, is the single most important constituent of our galaxy. Well, it did that job, and it did it extremely well. But at most telescopes that have been built, it's not just the reason they were built for that makes them famous, but it's other things, the serendipitous discoveries. And of course, the commissioning of this telescope in 1961 coincided with the discovery of the quasars. But at the time it was built in 1961, we didn't know what the quasars were. They'd been discovered as radio objects emitting large amounts of radio energy, but there was nothing there at the same position on the sky. The reason is that the positions were not accurate enough. And in order to pinpoint positions accurately, it was necessary for telescopes, radio telescopes, to do something very special. One way we now use is to use two telescopes to get greater accuracy. But then that was not possible. The principles of interferometry, as we now call it, just weren't advanced enough. So this telescope did something very, very clever. It actually used the moon to occult 3C273, one of the strongest of the radio objects, and in so doing, by precisely timing the instant at which 3C273 disappeared behind the moon and reappeared out the other side, it was possible to give an exact position for it. And that led to the discovery of 3C273 as an optical image and the first of the quasars. Though that was not enough, this telescope for many, many years was the only radio telescope in the south. And therefore it had the job of surveying, well, half the universe, you could call it. And starting from its earliest days in 1964-65, and then again in the late 1970s, during the 80s, it performed major surveys of the sky, discovering very many radio sources. Finally, the one I think that gives me the greatest pleasure, though I wasn't involved with it at all, was the discovery of the Magellanic Stream, to find that our galaxy was connected to the nearest galaxies, the large and the small Magellanic Cloud, by a bridge of neutral hydrogen, was a discovery made by a team largely of optical astronomers from Mount Stromlo, using the Parkes telescope, but not the large Parkes telescope, but a smaller one that's adjacent to it. And in this way, they mapped it out in neutral hydrogen. And it now seems clear that the Magellanic Stream is a bridge of hydrogen that's been pulled out of our galaxy by the Magellanic Clouds passing nearby.
How does the design of the Parkes dish compare with that of the Lovell telescope at Joshua Bank?
Well, there's a lot of similarities and there are a few differences. The similarities are that they're both great telescopes, probably the most productive, efficient telescopes in both the northern and the southern hemisphere. The Lovell telescope, of course, was a little bit earlier. It came online, I think, around 1957, whereas this one was 4 years later in 1961. But they're both large single-dish telescopes, and the thing that single dishes do best of all is collect a huge amount of energy, and they can see reasonably fine detail. But for very fine detail, we need to go down to the array-type telescopes, where a lot of telescopes work together.
As you say, the Parkes telescope is now quite old. How do you keep it in the forefront of radio astronomy?
Well, the skeptics say that it's a question of the old axe that's had several new blades and several new handles. That's not quite true. The reason the Parkes telescope has been so very productive over the years is simply that it was so well built in the first place. Of course, a lot of the design innovation came from Barnes Wallis, the man of Dam Buster fame and the Wellington bomber fame too. But probably his greatest lasting monument is not the Dam Buster bombs, but is in fact this radio telescope. telescope. And this radio telescope has been so well done that we've been able to improve its surface, we've been able to make modifications to its drive system to bring it up to a telescope which, although it was only planned to have about a 15-year lifetime, has done far better than twice that. And we envisage that it's going to be for several years more.
We've been hearing a great deal about pulsars. One particular pulsar has just been causing considerable interest. It's a member of a binary system, and it's in orbit around a hot star that we can see. Its path around the star is elliptical, and the two are now just about at their closest, so we're expecting some very interesting interreactions.
We know that quite often massive stars come in twos and they orbit about each other. We also know that massive stars end their lives in these supernova explosions. And when the supernova goes off, what gets left behind is this tiny little star that we call a pulsar. And it's only about 10 kilometers across, but it still weighs 1.5 times the mass of our sun, so it's an incredibly dense object. Now, we also know that supernova explosions are very violent events. So quite often, the two stars will separate during the time of the supernova explosion. But if we're very lucky, the pulsar may remain in orbit about the massive star. Unfortunately, again, these massive stars have very strong stellar winds, and it makes the pulsar very difficult to see in radio waves because they get blocked out by the material coming off the big star. However, in this case, we happen to be very lucky in that the pulsar is in a very elliptical orbit, and that means for quite a lot of its journey, it's a long, long way away from the big star. And that means that the radiation, the radio radiation, can get through to us. The pulsar takes 3.5 years to go around the big star, and over these next 2 weeks, it'll be very close to the big star, and the distance is about, the distance from sun to Venus is about the closest they'll approach each other. And so this is a very exciting event for us.
Is it the first time an event of this kind has been observed?
Yes, it is, because this is the only radio pulsar known to be orbiting a massive star. And because it's in such a long orbit, it was only discovered 3 years ago, and so this is the first time that we'll observe this closest approach.
What's the importance of this particular binary pulsar?
We've observed already 2 massive stars in a binary orbit. We've observed X-ray binaries, where you have a neutron star and a massive star giving off X-rays, and we've observed double neutron star systems. Now, we think they're all linked together in some way, but we always had the missing link, which was a radio pulsar in orbit around a main sequence star, and this is exactly what we've got in this case. So this is the missing link between all those systems, and we think that's the way the systems evolve, so that's why this system is particularly interesting.
What's the present state of the event? What have you actually been observing?
Here at Parkes, what we saw was that the pulses from the pulsar disappeared about 2 weeks ago. And that's more or less as we expected, because as the pulsar gets close in to the massive star, the wind is occulting the pulses. However, we've been looking at the pulsar at Narrabri with the Australia Telescope Compact Array. And at Narrabri, we can see that there's a very strong source at the position of the pulsar. And it's about 5 or 6 times stronger than the pulsar normally is. So at the moment, we're trying to decide what exactly is going on.
One of the most important developments in radio astronomy is to use not one radio telescope alone, but a whole collection of telescopes working together, as with the Merlin system in England. The system over here is known as the Australia Telescope, and this great 210-foot dish at Parkes is part of it.
Radio astronomers have learned how to link the different telescopes in order to provide something with the capability of seeing much finer detail. Any telescope sees, a good telescope sees not only faintly, for which it needs to collect large amounts of energy because they're so faint from the edges of the universe, which is what we're often looking at, but also it needs to see finely. Now, Parkes is very good at seeing faintly, not quite so good at seeing the fine detail. For that, we need a large array of telescopes, which is what Narrabri is. But by having both our own facility and our sister facility at Narrabri, we've got the game pretty well covered, and we can do world-class radio astronomy.
The Australia Telescope is made up of several large radio dishes distributed around the southeast of Australia. The main array is here at Narrabri, 200 miles north of Parkes.
Yes, here at Narrabri we have 6 antennas, each 22 metres in diameter, and they're on a rail track so that we can actually move them anywhere over a distance of about 6 kilometres. These antennas each weigh something like 270 tonnes, and they can point with quite remarkable precision, something like a 500th of a degree for such big antennas.
How does the network work?
Well, we combine signals from these antennas spread out, as I say, over this fairly large distance by bringing the signals back to a central point on optical fibres. And we bring back about 2,000 million numbers per second from each antenna to do that combination.
What are the other elements of the telescope?
The other parts of the telescope are located much further away, and the idea being that the bigger the array, the finer the detail you can see. So we can combine the signals from these antennas at Narrabri with others at Coonabarabran, Parkes, Tidbinbilla, Hobart, covering well over 1,000 kilometres, and indeed with antennas in other countries, giving us effectively antennas almost the size of the Earth.
How do you combine the signals from the various elements?
Well, of the elements that are located here at Narrabri, we combine them in a very special supercomputer which does something like 2 million multiplications per second. But when we want to combine the signals from the more distant antennas, we have to bring tape recordings of the signals back to a similar computer and play the recordings back. And then the processing goes pretty much the same way as it does here in real time.
Obviously, your tape recording has to be very accurate. How accurate?
We have to get the timing between the signals from the different tape recorders accurate to about 1 part in a millionth of a second, which of course requires that we have atomic clocks at each of the telescopes. The tape recorders themselves are banks of video cassette recorders so that we can record the enormous quantity of data that we need to achieve the sensitivity that is required of these observations.
I well remember that in the early days of radio astronomy, the trouble was a lack of resolving power, a lack of resolution. That certainly isn't the case today. How did you solve it?
Well, over the years, radio astronomers have, of course, been able to build bigger and bigger antennas, but there comes a point where you can't build bigger antennas to achieve higher resolution. So the problem has been solved by the process we use here at Narrabri of having antennas spread out over a large distance, kilometres in this case, but hundreds of kilometres when we combine signals from the more distant antennas.
In 1987, a very important event occurred. A supernova flared up in the large cloud of Magellan, unfortunately too far south to be seen from anywhere from Europe or the continental United States. It was discovered in Chile, and we've done many broadcasts about it. Obviously, it's being closely followed from here at Narrabri, and in charge of the observations is Dr. Lister Stavely Smith.
The advantage of observing at radio wavelengths is we can image the outer shock front that was set off by the supernova in 1987. And this shock front is currently moving at a speed of about 30,000 kilometers a second, a tenth the speed of light. And the radio regime is the only wavelength at which the outer shock front can be seen at the present time.
What are the latest results?
Well, the latest results from the compact array are shown in this image here, which shows the expanding remnant of the supernova to basically have a shell-like morphology, and the diameter of that shell is consistent with an expansion velocity of about a tenth the speed of light. But there are two hotspots to the east and west of the supernova, which we believe are associated with the optical appearance of the nebulosity around the supernova.
What about interactions with the Hubble ring? And what is the Hubble ring anyway?
The Hubble ring was obviously made famous by the Hubble Space Telescope, and it's a ring of material, a very small ring of material located around the supernova, and pictured in this image here from the Hubble Space Telescope, and shows the circumstellar material that was ejected by the star before it went supernova. The supernova is in the middle of this image here, and the ring is lies around the supernova. It's actually a circular ring, but it's tilted with respect to our line of sight. And this ring was illuminated by the ultraviolet flash from the supernova when it went bang. And when the shock front from the supernova, as imaged in the radio, catches up with this ring, there will be some fireworks in the optical and in the X-ray regime, and of course in the radio regime.
When will that be?
That's likely to be at the end of this, towards the end of this century. The date of about 2005 has widely been quoted, but our recent results tend to suggest it'll be somewhat before then, maybe 5 years before then. So the end of this decade looks the most likely date.
So far, no definite sign of a pulsar.
No definite sign of a pulsar yet, various false alarms, but as yet no sighting.
I think I'm right in saying that the real importance of this supernova is that you're going to be able to go on studying it for years, which of course with a supernova in a remote galaxy you can't because it fades.
Yes, indeed. This supernova is about 100 times closer than the closest supernova we've seen in recent times, and therefore we can follow the radio evolution of this supernova basically until it becomes a supernova remnant, which will occur in about 100 years' time. So over a very long time span we can follow the evolution of this remnant and study the way that supernovae interact with their environment and supernova remnants are formed.
When most people think about radio astronomy, they think of traces on a graph, but you're getting pictures.
Yes, what we're working with now is a synthesis telescope which uses the Earth's rotation to form a two-dimensional image over a period of 12 hours. So after a 12-hour observation with the Australia telescope, we get a picture.
The whole Australia telescope project is very exciting. It's also very new, isn't it?
Yes, the Australia telescope, though, comprises the old Parkes 64-meter telescope, which you've already been looking at, and two new components. There's a compact array here at Narrabri, spread out on a railway line, so that they can be spread out to 6 kilometers, which is what you do when you want very fine detail on a small object, or you can run them in on the railway line, so you get a wide angle, and then you look at large objects with low resolution. And then the third component is the ability to combine Parkes, the Narrabri compact array, and a new telescope at Mopra to form what we call a long baseline array.
What particular types of objects are going to be the main targets?
Well, since these are the main radio astronomy facilities in the Southern Hemisphere, obviously anything which is unique to the Southern Hemisphere is very important. So there's the center of the galaxy, obviously the Magellanic Clouds, and in fact the nearest radio galaxy, Centaurus A, is also at minus 45, so very much a Southern Hemisphere object.
What are the ultimate aims?
Well, for the moment, this kind of research, people think of the questions of the structure of the universe, problems of the missing mass, and then of course there's always this intriguing question of what powers the nuclei of active galaxies. Are there black holes there?
What have been some of the latest results?
Well, just last night we were making one of the very exciting observations of the supernova remnant, which is now forming around the location of the supernova 1987A. Another example is here in the galactic center. This is an image which was made with the MOST synthesis telescope of the galactic plane. Right here in the middle is the center of the galaxy, and there's a rather inconspicuous little region. When that was imaged with the Australia telescope, it was found to be this very strange object which has been nicknamed the snake. There's nothing like this been seen before anywhere else in the galaxy, and there's a great deal of argument about what can possibly be making this kind of object.
When you say images, you mean, of course, radio images, not optical images.
That's right. A telescope like the compact array here at Narrabri is done this way in order to achieve the resolution of an optical telescope at radio wavelengths, and it builds up what we refer to as an image, but in fact it's all made at radio wavelengths. But it has the same kind of detail that you expect in an optical photograph. Another example which has resulted from the versatility of this telescope is being able to observe at some frequencies which have not been available before. And around 6 gigahertz is a methanol maser has been discovered. And one of our scientists has recently discovered a very unusual situation in that these methanol maser spots form a line on either side of presumably a star which is in the middle. And it's just possible that this could be an indication of a protoplanetary disk, and these might be the regions of planet formation.
What exactly are methanol masers?
Well, methanol is wood alcohol, a form of alcohol, but it exists out in space. And some of these molecules in space maze. That is, in the same way as a laser amplifies light, a maser amplifies radio waves. And the methanol molecules have inverted populations of their spectra, and they can amplify the waves and make them very strong. So it's very easy to see this particular kind of molecule using the radio telescopes, even at very great distance.
What about jets in galaxies?
Well, we have a very exciting result on jets in galaxies. This object here, which was observed last year, is a giant radio galaxy, and in fact the jet has been seen extending all the way over a region which is 1.5 million light years in size, and that's now the record as the longest jet which has been seen in these radio galaxies.
Are you working in conjunction with other arrays, such as Merlin in England?
Well, of course, as you know, Patrick, with the very long baseline technique, we can combine with other telescopes anywhere in the world, but the other telescopes have to be able to see the same object at the same time. So unfortunately, Merlin is on the other side of the world, so we don't have objects that we can both see. So when we combine with other telescopes, we are developing a network of telescopes in the Asian Pacific region, in particular telescopes in China and Japan, and we can also combine with telescopes on the west coast of the US. Perhaps even more exciting for the future is combining with telescopes in space. The Russians have the Radio Astron program to launch a telescope in space, and the Japanese have what's called the VSOP project to put a telescope in space. Now, once the telescopes are in space, they see objects in the north and the south, and so, of course, they very much need telescopes in the southern hemisphere. And so the telescopes, which we've just been talking about, Parkes, at Narrabri, and at Mopra, will be very important for linking with these space telescopes for observing any of the southern objects.
We've had plenty of optical telescopes in space, including the Hubble Space Telescope. But so far, there haven't been any really big radio telescopes in space.
These will be the first, except for some very low frequency observations that were made with radio telescopes in space some time ago at frequencies which were too low to get through the ionosphere. But this is the first real radio telescope in space, yes.
Is the Australia telescope as good as you expected?
Oh, yes, it's been performing extremely well. And we have scientists from all over Australia and from all over the world coming here making observations. And so we now have in the southern hemisphere a high-resolution imaging radio telescope which can complement all the fine optical telescopes in Australia and Chile.
Half a century ago, there was only one intentional radio telescope in the world. That was in Tasmania, built by Grote Reber. Today, radio astronomy has become one of the most important branches of modern science, and Australia remains in the forefront. This great new network has already proved its worth, and in the years to come, it will do a great deal in helping us toward a better understanding of the universe.